yesterday's project. Okay, so first of all, I'm just open up the project where we have been actually left. So I hope you have been remember the concepts and all, guys. Yesterday we completely study about the all basic fundamentals of clock configurations, GPIO configurations, and we completed the ADC values we have to be acquired. Right. So the value is going to be sample and it is going to be converted to analog to digital values. So we have to be convert the analog signal to the digital signal. So analog to digital converter. Sorry, it's a digital data. So it need to be converted the analog to digital. So in this case, we have been completed the analog to digital data. Okay, we are having certain analog to digital data. Okay, so that data we have to be send it to the other microcontroller, that is the Arduino, through your communication protocol. Okay, through your communication protocol. So these are the different datas I might be having. So like these are the digital data. Okay, I have converted the analog to digital converter. So if you want to understand about the detail about the analog to digital converter, so it is in our previous day recording. So you just watch that. What is the analog to digital converter and why we call it as an analog, why we call it as in digital. Okay. In this case, I'm having a digital data, so it should have the multiple data, right? So because I just sampled, I just having the multiple of data. It might be each and every data is in the range of 0 to 4095 because it is a 12-bit ADC. You can able to acquire this range because it's a 2 to the power of 12, maximum 4096. You can able to get 0 to 4095. So each and every data would have this range. That data you are going to be send it to the other microcontroller. That is, we are choosing example Arduino have been chosen with the help of this UART communication protocol. So you have to be sent the data. So each and every data. So once we have been sent this data, what is the time duration it is actually going to be taking for other data going to be sent? So this data has been sent. For example, you just consider it is a 475. This is the digital data I'm going to be sent through UART communication protocol. Okay, the first data has been sent. So what is the second data going to be sent? What is the actual time duration between the first data and second data? So that we have to be implemented, we can use for the timer here. Okay, with the help of the timer, we are going to be generate the delay. So which is actually going to be make after you have been sent the 475, it will be take 1 second or somewhat you can consider millisecond. After that, other data, like for example, 576. So this data is going to be set. So this is the actual thing we have to be implemented on today because up to ADC we have completed up to yesterday. So we have to continue the USART and other one is the timer we have to be implemented. Okay, so yesterday also we completed the MODA registers for USART. So why it is actually considered as an alternative functions. Okay, so now we will continue where we have been left yesterday. So don't worry, Hemandra, you can because you already purchased this courses and all, so you can able to see it in the recorded sessions. No worries. Okay. Okay, so here this is one we have to be use it for the data sheet. I'm just simply open up the data sheet. Okay, in this data sheet, yesterday I told you all things like we need to configure the GPIO pins and all. So first of all, you have to be set the you have to be required the timer 11 and UART 1 and finally ADC 1. So these are things you have to be configured. So this has been done yesterday and we have to be configure these two things. Okay, so we have to call it as in timer, guys. Okay, so here the thing is the USART one first of all will complete and then go to this timer 11. Okay, first of all USART one we consider it as connected with which bus And after you have to be find it out this USART one which is connected with which GPIO pin. So yesterday itself we just find it out USART one is connected with the port T of ninth pin and timer B it has been connected with somewhat port B of ninth pin, right? So we have been find it out for both the pins. If you have missed out, you just go and watch that one, guys. So you just simply go to the pin definitions and then you have to be get this which pin it has been connected and all. Okay. So after you have been check it out, you have to be enable the clock for port A and port B. After you have been enable the clock, you have to be set to the mode, which mode it task going to be performed, input or output alternative, you have to be set. So up to that we have been completed. Today, it has been set at the moda register. So in this USART, if you are going to be checked, USART has been set at the value of C10. Okay, that's what it is, the 2. Okay, and we will continue after the alternative functions. So here I'm just go to the moda function. Okay, this is the GPIO moda. This moda for every peripherals, whatever the peripheral you are just configuring, definitely moda going to be performed before because with the help of the GPIO pins only, you just configure, you just interface with the peripherals and all, right? You have to be tell whether it is input or output or alternative or analog. Definitely you have to be configure this too. So USART comes under the alternative, analog ADC comes under the analog and timer comes under the alternative. It is going to do the multiple function. So since it is having alternative function of USART, you have to be configure the value called as 10. So 10 we have to be write in this form of 2. Okay, so 2 means one binary value. We have to be written in this number logic. So it is called as 2. And how many times you have to be shift the bits? You have to be shift the bits up to 18. Why? Because it is located, the mode R9, it is located at the 18th position. So I'm going to be shift the bit up to 18 times. Okay, that's the logic. So I will set the bit called as 10, which is called as 2. I'm going to left shift up to 18 times. So this is the logic which you have been written. If you ask why you written like this, so this is just to reset the bits. What is the meaning of 3? 3 is 1, 1. Binary value 1, 1. So if you want to simply reset the bit, sometimes it might be some other bit might be already set conditions. If you want to be clear out the things, you can simply put reset the bit. You just give a 1, 1, make it 1, 1. And if you're just using a not operator, everything gonna be resetted. Okay, this line of bit is get resetted. That's what we have been used here. Reset the bit. And after you have only set the bit. Okay. So after you have been set the more alternative function, so you always remember that whenever it is a alternative function, you have to be map the values because it is having the multiple function like tx, rx. Okay, so it is having a multiple alternative functionality. It is holding that. Okay, because we are going to be set to the 10 for both. If you're here not using a rx. Yes, yes, exactly, Prashant. So you have to be checking out this value of here, guys, not here. This is position. Okay. So this is consider this is exact position just for the namesake. It is only the pin mentioned. Okay, this is what the pin mentioned. So you always look out the table column inside this value. This is mentioning the pins. Okay. So after I've been settled out this value, it is doing the alternative functional mode. Okay, it is actually doing the alternative function mode. I'm having a multiple functionality going to be performed. So for that, I need to mapping the values. Okay, so for to mapping the value, same thing. I just duplicated the thing, guys. Okay, so mapping the value for you can able to see even in the GPIO mode R section, you can able to see this AFRL, AFRH. Okay, so in this AFRL, there is a two types of things. One is AFRL, another one is AFRH. So what it is actually to mentioning here it is. So whenever you are using your GPIO pin, whenever you are using a GPIO pin with a range of 0 to 7 or 8 to 50. Okay, so you are choosing a 0 to 7 whenever it is doing alternative function mode. Okay, alternative function mode. If it is your pin, the pin exact pin which have been chosen in this range, it is our AFRL. That is a alternative function of low. Okay, and if it is above than 8 to between 8 to 15, it is alternative function of high. Okay, there is a two types of ranges are there. Okay, one is AFRL and another one is AFRH. So there is the two types of things are there. So based on the pin you're going to be choose, since I'm using a GPIO of pin 9. Yes, I'm using a GPIO of pin 9. So for that, what I'm going to be choose, I'm going to be choose the AFRH. Okay, I'm going to be choose the AFRH. I'm going to be choose. So in this, when I'm just open up this is the AFRL. I'm not going to be choose. This is the AFRH. So in this one, what bit I'm exactly going to be choose. So how can I found it out is you just go to the data sheet. In this pin, you can able to see that alternative function mapping. So this is for just pin find it out. If you want to be find which exact GPIO pin, so don't confuse it. So always, yeah, if you want to be get the which GPIO pin your peripheral has been connected, it is pin definition. It comes under the pin definition. For to be find it out the pin exact pin number. Okay, but if you want to after find it out the pin, so the pin going to do the multiple functionality. Okay, if you want to be mapping the pin, for that you have to do the alternative function mapping for this. Okay, you have to be open up this, and here I'm going to be choose the GPIO of 9. So use that one of TX. Okay, so I'm not going to use RX. Okay, because I'm just transmit the data. Here I'm going to be map the value of AF07. This value I'm going to be implemented on here. So AF, what the value I need to be set? AF07. So this is the value. Okay. AF07, what the value it is holding? 0111. This thing, this value I need to be set at the position of AFRH of 9th pin. So 0111. Okay, I'm going to be set this value on here. Okay, so whenever you are going to be doing the more bit operation, first of all, you just reset the complete bit. Okay, since it is having a 4 bits, it just mode are just having a 2 bits. It is having a 4 bits. I'm just considering. First of all, I'm just taking this 4 bit. So which value, which binary value, which is just holding a 4 ones, like not exactly it's a binary value or decimal values or decimal. So in hexadecimal value, in F in the binary value of 1111. That is, we call it as 15. Hexadecimal, we call it as a 0 cross F. Okay. So the exact value of 15 is 1111. So I will get four 1 bits. Okay. So after that, first of all, I'm just set the 1 on this position. Okay. So first of all, I'm just simply set, not going to be set, I'm going to be reset it. Okay. I'm just put the not operation. So along that, you have to do the AND operation. Whenever it is a reset condition, when you want to be reset the bit, you have to be use AND or whenever you want to be check the condition, whether the bit flag is set it or not. Whenever it is a checking condition, you have to use the AND operation. Set the bit, you have to be use the OR operator. So these are the very mandatory questions, mandatory things. Okay, basic fundamental. So first of all, I'm just using 111 and just reset the value. I will get 0000. So 0000, I'm going to be move up to, I'm going to be make left shift up to 1, 2, 3. Sorry, exactly the position you just check it here. So 1, 2, 3, 4. Okay, so I will get up to 4 times. Okay, I'm gonna shift the bits up to 4 times. So 1, 2, 3, 4. So 4 times I'm going to be shift the bit. Also the position also same. So first of all, I'm just reset the bit. Okay. First of all, I'm just completely reset the bit, and after I'm going to be set the bit. So if I want to set the bit, the binary value, it is 0111. I'm going to be converted into normal value. It is considered as in 7, right? So normally consider 7. 7 going to left shift up to 4 times. So here I'm going to be set the bit. I'm going to be using a OR operator. So this is the thing which we had been done on here. Okay. So after that, we had studied about the UART and all. So now I'm just directly go to this UART peripheral, because we have to be completely work on this UART. So you just open up the introduction part and you have to be start to read each and everything. So what is UART? What is USART? Difference between UART and USART? And it is completely full duplex communications, and what the baud rate using fractional method it is going to be performed. And there is what are the technology you can able to interface with that, and high speed communication thing is possible. So everything you have to be read out in the features. Since we have to be write the code, so you have to be aware about the what are the errors can occur. Okay, for error detection flag, we can use a parity error or frame error, noise detection error, over an error. So other than that, we can also find it out to uh, errors and with the help of the something. So like parity control bits. So you have to be transmitting the parity bit. You can easily find out whether the sending data is right or not. Okay. So also, so there is a many things you have to be concerned about here. Okay, so we have to be directly transmitting the data. Now we'll concentrate on this. And after this, you have to be study about the 10 interrupt source with flag. So what it is. So transmit data register should be empty. So these are the causes some interrupts. Okay, transmission completed. So I already told you that not only the interrupt is completely hardware based, or so internal interrupts is also going to be possible. So these are considered as an somewhat internal interrupt. And here the user functionality has been described here. So the transmitting data and receiving data, and what about the data words? What is the ideal line and start bit, data word and stop bit, and a status condition, final data register and baud rate. So it is complete thing. And you just scroll down, scroll down, scroll down. Here I can able to get the transmitter. So why I'm going to be is choosing this transmitter, I need to be specifically get the procedure of transmitter, because I'm going to be transmit the data actually from my microcontroller, which is STM32. Okay, STM32 going to be transmit the data, and Arduino going to be receiving the data. Okay, and here I have to write the receiver code on the Arduino and a transmitter code on this STM32. While if you just see this Arduino code, it is very simple. So if you want to be communicating in this pure communication, the serial dot begin, which is everything here, but not like in your STM32. You have to be set the baud rate, set the start conditions, stop conditions, everything we have to be make sure correct. Okay, so that's the difference between these two. So first of all, what you have to be do it on here. So enable the USART by writing the UE bit on the CR1 register going to be becomes 1. So I'm going to be set the yeah, it's just telling like USART CR1 where the CR1 is there. That is the control register. We just go to this USART part, and here it is specific column called as in registers. Just find CR1. Here there is a CR1. Here, what you are going to be set, you have to be set the UE bit. What it actually going to do, enable the user. Yesterday, we studied about the add-on bit. Add-on bit is everything to enable completely enable the ADC. Okay. So inside your microcontroller, if you want on the ADC, you have to be on the add-on. Off the ADC, you have to be set 0. So on, make sure if you want to be on the ADC, you have to be enable that. Likewise, if you want to enable the user, okay, whether it is transmitting or receiver, so you have to be enable the UE bit which is presented at the CR bit. So same, which is like same. Okay. So here you need to be enable the UE1. Okay. That is first thing. So if you want to enable this UE1, so which is the CR1, you can able to see that I just shifted the bit up to 13 times to set the bit 1. Okay. UE1 you are going to be set 1. So for that I'm just shifted up to 13 times. I just shift. Okay, so this is one of the logic. Okay, you have been did here. Then what about this? So we'll see this one. Okay, so after you have been set this value, so you have to be set the M bit in the CR1 of word length. So whenever you want to be write the what is the length of your word. So when you're going to be considering about the length of the word, you have to be set the bit of M bit which is actually presented under CR1. Okay, so if you want to define the word length, if you're sending one string or what, so if you want to define the size of word or thing, you have to make sure you have to do this, enable the M bit on there. Okay, got clear? Yes. Okay, guys. So the thing here, it is USART one has been actually we have been first of all enabled it, and then we are just simply doing the bit we have been set it. If you wanted it, if you want to define the word length, if you don't want this, you don't want to enable this. And finally, you have to be number of stop bit. Here, just asking you program the number of stop bits in the USART in USART. Okay, like here it's just telling if you just go to this use CR2, how many number of stop bits you exactly want. So if you want defining the stop bits, I want one stop bit or I want two stop bits. So these stop bits are used for programming the stop. So in program wise, we just use the stop bits, whether you want 1 or 0.5 or 2. So basically, we are going to be using common one stop bit only. Okay. So, and if you are configuring a DMA, okay, here we are not using a DMA, direct memory access without processor, just transmitting data. Here we are not going to using that. Just skip out this, just skip this one. Okay, so this also we are not using, and this also we are not just configuring the stop bits and all. So it is going to be automatically once you have been transmitting. Okay, we are not stopping the. So why when we are going to be stopping the bits, it is actually going to be do like so one set of data frame is going to be selected. Okay, so based on the baud rate you are going to be using on here. So here I have used the baud rate. So next thing is I'm going to use the baud rate with the help of the BRR register. So in this BRR register, where it is actually located, it is located at this here. Okay, here there is a two types of thing is the div mantissa and div fractional. So you can able to check on here. So I need to calculating the value. Okay. So why I'm going to be need to calculating the value of clock? Because if it is a baud rate only, okay. So here the fractional baud rate generation has been given. So whenever it is a baud rate, if you are using a UART only, you have to be work on with the baud rate. Okay, what if you are just want the 9600, you simply convert it into the hexadecimal value and use it. So because if it is a USART, okay, USART means it requires the clock plus baud rate. I need to be set what clock frequency it is actually going to work plus baud rate it is going. So for that I need to implement it to this formula like baud rate. So here the TX and RX baud rate you have to be used. For example, 9600 I'm going to be used. And the clock frequency, what clock frequency I'm going to be used? Here I'm going to be using a 16 months. So for internet, this applications and also I'm going to be using the 16 megahertz. We have been studied in the data sheet. So we are going to be using the 16 megahertz. So I'm having this data, need to find it out the user division. So you just change the things and you just simply doing like 16 megahertz divided by 16 cross 9600. So you will definitely get 1 year and which is actually making like 1 megahertz into 1 megahertz divided by 9600, you will get some value. Okay, you have to be calculated the value. And finally, when you're going to, when I'm going to do this calculator, convert it to this hexadecimal value. So 0 cross 682. Okay, the value which you have been given, that value you have to be to the hexadecimal value. Okay, just to convert to this hexadecimal value, and you just implemented it. Okay, that's the thing. I've been uploaded. I've been updated that value. Okay, here it is a receiver. So I've been updated the baud rate and all, and after that set the TE bit in CR1 to send the ideal frame as first transmission. So this is the first thing for just telling like to send an ideal frame as first transmission. It is the transmitting enable, okay, which is actually in the CR1, okay, which is actually in the CR1. So which is actually in the CR1 of TE bit. Okay. In this TE bit, I'm going to be set up to, so I'm going to shift up to 3 times, 1, 2, 3. Okay. I'm going to shift up to 3 times. So this is different. This is completely enabling your UART, user. Okay. This is enabling the transmission. So here you can, if you are not, if you don't know this, you just study from here. So this is telling like transmitter enable. This bit enable the transmitter, it set and clear the software. So it is actually doing like enabling the transmissions. Like while you're going to be setting this bit as 1, it is actually creating the pulse 0. That means start conditions is 0, pulse 0. So it actually telling like starting the communications, right? Okay, so this is what it is actually going to be performed. So that is also done. So since it is holding the same register, we can easily make it like I need to set the bit. Okay, one is UE, another one is TE. Okay, I'm just commonly doing OR operations. In this, because since it is having the same register, okay, it is having in the CR1 of same register. All the thing has been there. One is UE, another one is TE. Okay, so UE has resided at this 13th position. Okay, like 0000. And other thing is TE has been located at this third position. So all the bits are 0. So when you're going to do this operation, you will easily get some value and you can implement it into the register. So the register is actually going to be enabled the UE as well as TE. So when you're going to be enabling the USART, same time you start transmitting the okay, actually the data has actually started to be transmitted. Both has been done at the same time. Okay, this is what we have been done. Okay, this USART one initialization. So we have been done the initialization. So after you have been initialization has been done, what will be the thing? So start the condition, data you are going to be sent, and a baud rate. Finally, you have to be stop the condition. Start, we have been started, baud rate also been set. Now we have to be the data we need to be set. What data we are going to be set? So what the data which we are get from the temperature sensor, that is the ADC. Okay, so analog to digital converter, which is actually doing that digital value, we have to be sent as a data through user communication to other microcontroller, right? So that data we just get it and send. So for that one, we just return the another special function. Here I just declared another function. It is USART one of send60. So you just create any function. Here I've been created this function. Okay, and inside this, I'm just put value. So what the value which I've got on this ADC one? Okay, the value which I've got is yes. So ADC value. So this is the value which I've got. Final data. This value I'm going to be sent to the microcontroller, other micro. Right. So what I've did simply, I just pass this value to this function. Okay, and just simply pass this value as an input to the USART1 function. Okay, just consider it as an input and it just taking this input. After taken this value as an input, we have to be check the condition. Here, if you just study this one, so after you just send the data, this is the very, very important point you have to be concerned about this. Here, write the data to send it, use out of data register. So what is actually telling, write the data to send it, use out data register. So in this data register, you are going to be send the data because it is just holding the data. Okay, whenever you want to be read any data from system to send it is just a holder. Okay, just having the final output data going to be a hold on this data register. So it is going to be sent the data through this DI. But the thing is, this clear the TXE bit repeat this for each data to be transmitted in case of single buffer. So what this actually means is, so this is the flow you have to do. This final data is going to be stored on this data register, DR register. Okay, it is actually holding the DR register. The final data is going to be holded. Okay, so it is actually going to be sent to the other microcontroller. Yeah, it is going to be do. But if you want to send to the other microcontroller, it need to be checked whether the buffer is free or not. That is a TXE bit. So if it is buffer is free, it is going to be sent. If it is not free, just holding the data. This is the checking condition. So here they didn't give the condition like you just set the TXE bit. This telling like this clears the TXE bit, repeats the for each data to be transmitted in case of the buffer. Okay, so that means if you want to be write the data to this DR register, first of all, this actually going to be clear the TXE bit. Repeat this for each data going to be transmitted. So when this condition going to be happens repeatedly, we can't always going to be clear set. Can you able to do this with the help of this for loop? No. So it is not going to be do this. It is not a worthy function. Okay, so it is not a worthy function. So in this case, we can write as a conditional stage. Okay, so conditional or checking stage, we can call exactly it as a checking condition. Okay, so when the TXE bit is free, okay, we can send the DR data going to be send the data, the value which is actually old at this value. Okay, so here I just tell you that TXE bit we can able to send. So it is that you have to be find it out where this TXE has been presented. I'm going to be search where this TXE has been presented. Here the status register, you will have this TXE. Okay, so it's wait a minute. Okay, the TXE bit I'm going to be set. Not I'm going to be set, I'm going to be checking on this. So here you can able to study the transmit data register 80. This bit is set by hardware when the content of the TDR register has been transferred into the shift register and inter-generated TXE bit is going to be 1. In the CR1 register, it is cleared by write DR register 1. 0, the data is not transferred to the shift register. 1, the data register transferred to the shift register. So first of all, what they are actually telling, this bit is set by hardware. So they have been clearly given that. So this bit is set by hardware, not by manually. So this is what I just yesterday tell you for the yesterday we studied for the EOC, that is the end of conversion. That is also having this code, like this bit is actually set by hardware. So hardware means once the function has been completed, once the work has been accomplished, once the work has been done, so it is automatically set by the hardware. Okay, so it is set by the hardware when the content of this TDR register has been transferred into the shift register. Okay, so an interrupt it is going to be done. So for this one, you have to be write it as a checking condition. So for that only, so I'm going to be using the status register of UART. Okay, I'm going to be use the status register of UART. I'm going to be use and I'm going to be do the OR operation. So manually, I'm going to be shifting the bit up to 7 times. Okay, one going to be shifted up to 7 times. When this bit, so when this condition has been satisfied, because this status register, inside the status register, this TXE 7th bit is automatically going to be updated. 7th bit automatically gets set by the hardware, not by user. Okay, not by users and okay, it is automatically set. So initial condition, it might be in the 000. So when it is 000, you manually trying to set 1. So it is at the 000. This operation has keep the 0 still 0. When the hardware which is actually making that 7th bit TXE bit is make it as 1, we have to be automatically set it. We have to be trying to manipulate the 7th bit trying to be set 1. Okay, we have to shifted the bit 1 at the position of 7th position. Now we have to do this operation. It will be provide the 10000. Okay, we can easily implement it. This condition is also get satisfied. Okay, here you can able to see. This is the checking condition we have it. Okay, it is actually continuously checking the conditions. Okay, got clear, guys? Got clear? Yeah, Mukesh Kambal got clear. Super. Here, the thing is, so this is just a conditional statement. Okay. Here we just end up with the semicolon. Okay, so yes, I'm going to be telling, right, guys. Yes, I am it. So here the thing is, here you can able to see it is a checking condition. Just for I just told you, it is for the checking condition, right? But in this, it is it is one loop. It is one. Okay, it is one loop. Here I didn't define anything else. It is one considered as a one loop. This line is only one. So what is actually when you do is until this bit has been set. Okay, if the bit is not settled, okay, it is in this line. So it is continuously running in this line. When it is actually not satisfied, so when it is going to be settled, the bit come out of this line. Okay, it is actually come out of this line and going to be store the data. Okay. So broken letters means okay, I can so okay, you can tell me clearly. So which broken letters? Why pointer is used in why? So here the thing is you're just asking why pointer is used. No, it is the bit. Okay, here you can see this one. Okay, here I'm having a USART. I'm using a SR register. Okay, I already told you that this is the address. Okay, of SR register. So if I'm going to define the pointer, if I just write the SR register and this is the address. So I can, if I'm going to be using the dereferencing of SR, which indicates I can use. Okay, so okay, I can able to like what can I say? So I can able to use all the peripherals which is presented on here. Okay, I can able to use. So I will try to reduce. I will try to write clearly, guys. Don't worry. Okay. So when I'm going to be using that pointer, I can able to fetch. I can able to use all the bits which is presented here. Okay. So first of all, I just use this status register of this one. Okay. So what it is actually mean that I can able to access. I have all the authority to use this one. Okay, so after that, I'm going to be shifting the bed piece. Okay, okay, nice idea. Thank you, guys. Okay, here you can able to see this one. So I can have the authority to use all the SR register. Okay, I can able to use all the SR register, right? So in this, in all authority I'm having. Okay, all bits I can able to manipulate it. Okay. All bits I can able to manipulate it. Okay. So in this time, what can I able to do this? So here I don't want this all bits. I have only the RXC bit, which is also automatically settled by the software. That's what I just simply declare. So if I'm using this register with the help of that address, I already written that. It is automatically this bit is enabled by the software. So I don't need to be configured. But shifting that bit, it is done by me. Okay. Because when this condition has been satisfied, okay, when it is automatically set at one, so I am easily doing this condition. Okay, I'm just easily doing like, okay, that has been TXC has been get free. Now I can able to transmit the data. So that's what I'm just store the data, the data which is stored on this DR register. Okay, the final DR register, you can also see it on here. Okay, so the data which have been which have been bought, I just sent through this USART of 16. Okay, so this is the function I've been used. Okay, so this is the function I've been used. So I'm just pass this data. So after I just pass this data, you can able to see this when yes. So here I just get this data on here. Okay, so after I just get this data, you have to be understand one concept. It is a 16 bit of data. Okay, so the ADC which is having a 16 bit of data are going to be sent. Okay, so it is actually sending the 16 bits of data, but this USART can support the 8 bits. So the data bit which we have been studied, maximum 5 to 8 or 5 to 9 bits only you can increase it. Since this ADC, not speaking about the resolution, it is 12 bit, no. It is a 16 bit of data. Okay, you can able to send the, if you just studied the data register of ADC, it is go to this ADC. In this ADC of data register, okay, they have been mentioned. It is up to 16 bits. Okay, this bits are read only bits and regular channel left or right bit. Okay, here they didn't mention. So here it is supporting a 16 bit. So here also mentioned 0 to 15. So it is there in this first line itself. Okay, it is a 16 channel bits. Yeah, here they have been mentioned. It is a 16 bit of data register. So what you have to be understand here, when the data has been manipulated, like you have been sampled the data, like analog to digital conversion have been made. This is the analog data and this is the digital data. Okay, so this is the 16 bits of digital data you have been converted. Okay, you have been converted for 16 bits, but you just check it. A USART support the 8 bit of data. So in this DR of data register of USART, which is holding only 8 bit, but the ADC of the data register, which is holding, it can capable of 16 bit. So both are just conflict, not exactly conflict. Both are just making some missing a data. Okay, so because it is sending 8 bits, it is. So in this case, how we can able to send the data? For example, I'm just having 1, 2, 3, 4. This is the data. You have to be consider each which is holding a 4 bits. So 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0. So if you just consider user, you just consider only the, okay, it is just exclude this one. So this time it is not going to be happen like this. You have to be send both the data, then only it is the complete ADC value. For this condition, we just split out the data into 8 bits. Okay, what we can do this, you just use this DR register. Through the DR register, we have to send the data. Take the value which you got from the ADC, the input value which you got the ADC, just to do the right shift operation. Okay, so if you just get one data, okay, you just simply making the right shift operations and just keep this position on here. Okay, so simply doing a right shift operations. Okay, actually you will get this value on here, and make sure you have to be do this what. So you just do this FF means you have to be masking with this FF. Okay, higher bytes, and you will get the higher bytes only. Okay, now you will get the higher bytes. And after you got this higher bytes, you will simply doing this one. So this value just simply having. Okay. So this value lower bytes. So here you will got the lower bytes value. So that value just simply masking with this FF, you will get the other lower byte value. Okay. You will automatically get the other lower byte values. Okay, so you can easily get this value, and finally you just transmit the data. So finally this one DR, this one DR. So both the data is going to be sent at, okay, so sent it so one after another. Okay, so after this you have to be make sure do the timer. Okay, so you don't need to be worried about that. Tomorrow we will discuss about this timer concept detailedly. Okay, so why it has been came. So what is mean by PSC values, auto reloaded values and all. We will discuss that. Now I'm just simply telling. So what is it is actually performed. So you know this up to here. So like what is we have to be enable the timer 11 clocks, and which mode is actually going to be do alternative function. So alternative function means it's definitely going to be map. Okay, so you have to be map the value. After that, timer enable you have to be do. Before timer enable, you just reset the value. Okay, after you have to do the prescaler value, auto reload value, and the CCR. So it is very easy. So when you are having some clock, okay, you have to be take a clock from your clock source of any crystal oscillator or any bus clock. Okay, in this time you have to be exact clock, you can't able to using. For example, in bus clock you will have 100 megahertz. Okay, you can't use the exact 100 megahertz. It doesn't require it. You just want some other clock you want required it. You just make sure you can divide the value. For that, you can use the prescaler. This is called as a prescaler. Okay, so you can able to use the value. For example, here I'm having the source of 100 megahertz. I only required the 1000. What you can do? You can simply do the calculation. So like 100 megahertz means I will get 1, 2, 3, 4, 5, 6. Okay, I will got up to the 0. For example, I required only the prescaler value 1000 means you just simply use the math of 5, that is 1, 2, 3. You just simply use the prescaler is by your own. Okay, you just define the prescaler, which is I just declare 10,000. Oh, sorry, 1 lakh. I just simply calculated, divided those values. Okay, finally I will get the 1000. So prescaler, which is always started from 0. So 0 to 999. Okay, so it is also considering, it is always count from 0 to 1000 or 0 to 999. Once it has reaches this value, it is automatically get stopped. Okay, so this is when. So auto reloaded value means this value just uploaded into this register 999. If you just upload the 999 or 1000, it just started to be counted all those values. So we will discuss all those stuff. Okay, detailing. I'm going to be tell you how to take these data from reference fund, everything. Okay, so no guys, both are different data types. You can see this data register we have been used for USART. This data register used for ADC. You can check the address also. It is not going to be get conflict. We just get that data from ADC. Okay, we just simply get the data from ADC through DR register and we just passing that value in the user function and app through this is the ADC DR register, and with the help of this user DR register we just send the data to the RDB or other any micro. Okay, now I'm just doing like connect my microcontroller here. Okay. So now I'm just so give me a minute, guys. I will make sure connecting all the components and wirings above. After we will proceed this. So now I'm just simply connect and start debug. So I just connected all those stuff. Now I'm just right click and debug it. So I hope you people are know how to debug this. You just select the project which you are doing. The project which I'm doing is temperature log project, right? So just right click. So this is the project I'm doing. So make sure you have to be enable this ST link and all. So this serial wire debug through this SWD. This is the serial wire debug. Make sure it has been connected with this connectors or jumper. Okay. So in your board and you have to be connect this ST link, which is the communicate like intermediate between the your controller and USB between them. So you make sure to enable the serial wire be over. So you have to be set the clocks and all, and finally just apply and debug. Okay. So I'm just simply doing an here you can able to see I need to be get the value. Okay. So you have to be make sure before going to be run this code, you have to be upload this code on this Arduino. First of all, you just set the baud rate. Okay. And here this code is very simple, guys. You can easily understand. Here I'm just getting a data like high B and low B. That means I declare two variables. First of all, I'm just reading high byte and low byte separately. After that, I'm just converting, I'm just getting the ADC value. I'm just make sure I'm just combine both the value because higher byte and lower byte in the separate manner. I'm just with the help of this OR operator, I'm just combining the both. After combine the data, I'm just converting into the normal data value, digital value to the Celsius value. Okay. So this is the formula to be applied for the converting digital value to the Celsius value. So I'm just now I'm going to be run this code. You can able to see the data on here and I'm going to be yeah, I can able to see the data. Here I'm just having a temperature value. Okay, here I'm using LM35. LM35 the temperature. This is the digital value. Okay, this is the digital data. Okay, so analog to digital conversion has been done first. Okay, this is the digital value. The digital value is actually converted into the Celsius. Okay, so this is how it has actually made the conversions and all. It is doing on here. Okay. So this is what the thing. So you can also, if you get the direct digital values is enough. Here I just converted the value to the digital to temperature. Okay. So you can able to see this one. So I'm just getting a data for every 1 second. Okay. That's what I've used the delay. Okay. Oh, you got clear, guys. So that's it. So the project which we have been done. So tomorrow we'll deeply discuss about the timer. So don't need to be worried about that. We'll discuss about the timer and for 1 second, for every 1 second, how it is actually made this event. Okay, so here I am just sending data. I'm just getting a data for every 1 second for each and everything which is having a making 1 second delay. Okay, which is making a 1 second delay. Okay, so yes, it is room temperature. It is somewhat loose connections or yeah. So that's what it just given this value. Okay, so here we have to be. So yes, guys, I can able to show. I am trying to show the hardware values and all. But the camera is not properly has been enabled, guys. So that's what I can't able to show it now. So So I'm simply telling you, so what the connection which I've made. Okay. So I'm just simply telling you that what connection which I've made. Okay. At the end of this slide. Here, after every 1 second, I'm just collecting this data. Okay. I'm just collecting this after every 1 second.